Long before the first rockets ever pierced the sky, long before any human being left the embrace of Earth, we were already travellers among the stars in our minds and in our hearts. Every civilization that has ever flourished beneath the canopy of night has looked upward and wondered. And so tonight we embark together on the most extraordinary journey ever undertaken by our species. We will trace the complete arc of space exploration, from those first wondering glances at distant lights to the footprints left in lunar dust, from the earliest dreams of flight to the rovers currently rolling across the rust-coloured plains of Mars. This is the story of how we reached for the heavens and against all odds began to touch them. Let yourself settle in now. Find that comfortable position. Let the weight of the day drift away from your shoulders. The story we are about to share spans thousands of years of human curiosity, decades of extraordinary courage, and moments of breathtaking achievement that changed forever our understanding of who we are and where we belong in this vast cosmos. We begin not with rockets or spacecraft, but with something far older and perhaps even more profound. We begin with the simple act of looking up. In the ancient world, the night sky was not merely a backdrop to human existence. It was a living presence, a realm of mystery and meaning that shaped the very foundations of human culture. The stars were not distant suns burning across incomprehensible distances. They were gods and heroes, animals and symbols, messages written in light across the dome of heaven. Consider for a moment the people of ancient Mesopotamia, living in the fertile lands between the Tigris and Euphrates rivers more than 4,000 years ago. These Babylonian astronomers were among the first to systematically record the movements of celestial bodies. They tracked the wandering paths of the planets against the fixed background of stars. They noted the phases of the moon with careful precision. They developed mathematical systems to predict eclipses, those moments when the sun or moon would temporarily vanish from the sky. To these ancient observers, such knowledge was not merely academic. The heavens were intimately connected to earthly affairs. The positions of planets influenced the fate of kings and kingdoms. The appearance of comets heralded great changes. The regular cycles of celestial bodies provided a calendar for planting and harvest, for religious festivals and civic ceremonies. Across the ancient world, similar traditions of skywatching emerged independently. In Egypt, the annual flooding of the Nile, that life-giving event upon which all of Egyptian civilization depended, was heralded by the heliacal rising of Sirius, the brightest star in the night sky. The Egyptians aligned their great pyramids with a remarkable precision to the cardinal directions, and shafts within these massive structures pointed toward important stars, perhaps intended to guide the pharaoh's soul on its journey through the afterlife. In ancient China, court astronomers kept meticulous records of celestial phenomena. They documented the appearances of comets, the occurrence of eclipses, the sudden brightening of new stars that we now know as supernovae. These records, preserved across millennia, remain valuable to modern astronomers studying the historical behaviour of celestial objects. The ancient Greeks brought a different approach to understanding the heavens. While earlier civilizations had been content to observe and record, the Greeks sought to explain. They wanted to understand the underlying structure of the cosmos, the mechanisms that drove the celestial dance. Aristotle proposed a model of the universe with Earth at its centre, surrounded by crystalline spheres carrying the moon, sun, planets, and stars. This geocentric model, refined by the mathematician Ptolemy in the 2nd century of the Common Era, would dominate Western astronomical thought for more than 1,000 years. It was elegant in its way, with its nested spheres and epicycles explaining the apparent motions of celestial bodies as seen from Earth. Yet even in ancient times there were those who imagined differently. Aristarchus of Samos, working in the 3rd century before the Common Era, proposed that Earth and the other planets might orbit the Sun. This heliocentric idea was too radical for its time, contradicting both common sense and philosophical assumptions about Earth's special place in creation. It would take nearly 2,000 years for this revolutionary concept to gain acceptance. The Maya of Central America developed sophisticated astronomical knowledge entirely independently of the Old World traditions. They tracked the cycles of Venus with extraordinary precision, incorporating these observations into their complex calendar systems. Their astronomical tables, preserved in the few codices that survived the Spanish conquest, reveal a deep understanding of celestial periodicities. In India, astronomers developed mathematical techniques for calculating planetary positions and predicting eclipses. The astronomical traditions of the Islamic world preserved and extended Greek knowledge during the medieval period, with scholars making careful observations and refining astronomical tables. All of these traditions shed something fundamental. They were attempts to understand our place in the cosmos, to find pattern and meaning in the movements of lights across the sky. They were the first steps on a journey that would eventually lead to rockets and spacecraft, to footprints on the moon and robots on Mars. But the path from ancient stargazing to modern space exploration required a revolution in thinking, a transformation in how humanity understood its place in the universe. That revolution began in the 16th century with a Polish clergyman named Nicholas Copernicus. Working quietly in his cathedral chapter, Copernicus developed a mathematical model of the solar system that placed the Sun, not Earth, at the centre. His great work, published in 1543, the year of his death, challenged more than a millennium of astronomical orthodoxy. The Copernican model was not immediately superior to the Ptolemaic system in predicting planetary positions. It still required circles and epicycles to match observations. But it was simpler in certain ways, and it planted a seed of doubt about Earth's privileged position that would grow into a complete transformation of cosmic understanding. The next great figure in this revolution was a Danish nobleman named Tycho Brahe. Working in the late 16th century, Tycho constructed the finest astronomical instruments of the pre-telescopic era and used them to make observations of unprecedented precision. His careful measurements of planetary positions, particularly of Mars, would prove crucial to the work of his assistant and successor. That successor was Johannes Kepler, a German mathematician with mystical inclinations and extraordinary analytical abilities. Kepler inherited Tycho's treasure trove of observational data and spent years trying to make sense of it. He was convinced that the cosmos must be constructed according to beautiful mathematical principles, and he searched relentlessly for the underlying patterns. After countless failed attempts, Kepler finally discovered the truth. The planets do not move in perfect circles, as had been assumed for 2,000 years. They move in ellipses with the Sun at one focus. This simple insight, combined with two other laws describing how planetary speeds vary along their orbits, finally brought theory into precise agreement with observation. Kepler's laws of planetary motion were a triumph of the new scientific approach, using careful observation and mathematical analysis to uncover the hidden workings of nature. But Kepler could not explain why the planets moved as they did. That understanding would require the genius of Isaac Newton. While Kepler was working out the geometry of planetary motion, another revolution was beginning in Italy. In 1609, Galileo Galilei heard reports of a new optical device invented in the Netherlands, a tube with lenses that made distant objects appear closer. Within months, Galileo had constructed his own telescope and turned it toward the heavens. What Galileo saw transformed astronomy forever. The moon was not a perfect sphere, but a world with mountains and craters. Venus showed phases like the moon, proving it orbited the sun. Jupiter was accompanied by 4 moons of its own, a miniature solar system that demonstrated Earth was not the only centre of orbital motion. The Milky Way, that faint band of light across the sky, resolved into countless individual stars. Galileo's telescopic discoveries provided powerful evidence for the Copernican model and against the old, Earth-centred cosmology. His advocacy for this view brought him into conflict with the Catholic Church, leading to his famous trial and house arrest. But the genie could not be put back in the bottle. The telescope had opened a new window on the universe, and nothing would ever be the same. The 17th century saw the flowering of the scientific revolution, with Newton's great synthesis bringing together celestial and terrestrial physics under a single set of mathematical laws. Newton showed that the same force that makes an apple fall from a tree also keeps the moon in orbit around Earth, and the planets in orbit around the Sun. His law of universal gravitation, combined with his laws of motion, explained Kepler's empirical rules and provided a complete mechanical description of the solar system. Newton's work had a profound implication that would not be fully appreciated for centuries. If the same laws of physics apply everywhere in the universe, then in principle it should be possible to travel to other worlds. The heavens were not a separate realm governed by different rules. They were part of the same physical universe as Earth, accessible to those who could find the means to reach them. Through the 18th and 19th centuries, astronomy continued to advance. Better telescopes revealed new planets, first Uranus and then Neptune. The distances to stars were finally measured, revealing a universe far larger than anyone had imagined. Spectroscopy allowed astronomers to determine the chemical composition of the Sun and stars, showing that the same elements found on Earth exist throughout the cosmos. By the late 19th century, the intellectual groundwork for space exploration had been laid. The universe was understood as a vast physical realm governed by knowable laws. Other worlds existed, some perhaps not entirely unlike Earth. The question was no longer whether space travel was conceivable in principle. The question was whether it could ever be achieved in practice. The answer to that question would come from an unlikely source, from dreamers and tinkerers who imagined using the ancient technology of rockets to reach beyond the atmosphere. The rocket is one of humanity's oldest inventions, with origins stretching back more than 1,000 years to medieval China. The earliest rockets were simple devices, tubes filled with gunpowder that produced thrust when ignited. They were used primarily as weapons and fireworks, entertaining and terrifying in equal measure. For centuries, rockets remained essentially unchanged, curiosities with limited practical applications. They were too unreliable and too weak to serve as serious tools of transportation. No one imagined that these sputtering tubes of fire could ever carry human beings to the stars. The transformation of the rocket from toy to spacecraft began with a few visionary individuals working independently in different parts of the world. These pioneers of astronautics saw what others could not, that the rocket held the key to escaping Earth's gravitational embrace. The first and perhaps most remarkable of these visionaries was a Russian schoolteacher named Konstantin Tsiolkovsky. Born in 1857 in a small village, Tsiolkovsky lost most of his hearing to scarlet fever as a child. This disability isolated him from normal social life, but drove him inward, toward books and imagination. Tsiolkovsky became fascinated with the possibility of space travel. Working in isolation, without access to the scientific establishments of Moscow or St. Petersburg, he developed the fundamental mathematics of rocket propulsion. His rocket equation, published in 1903, the same year the Wright brothers achieved powered flight, describes the relationship between a rocket's velocity, the velocity of its exhaust, and the ratio of its initial to final mass. This equation revealed both the promise and the challenge of space travel. Rockets could indeed achieve the velocities needed to reach orbit and beyond, but only if most of their mass consisted of propellant. A rocket bound for orbit would need to be mostly fuel, with only a small fraction devoted to payload and structure. Tsiolkovsky went further, proposing solutions to the challenges his equation revealed. He suggested using liquid propellants, which could provide higher exhaust velocities than solid fuels. He conceived of multi-stage rockets, which could discard empty tanks along the way, improving efficiency. He imagined space stations and described the physiological challenges astronauts would face in weightlessness. All of this work was theoretical. Tsiolkovsky never built a rocket. He was a dreamer and a mathematician, not an engineer, but his ideas laid the conceptual foundation for everything that would follow. Across the Atlantic, an American physicist named Robert Goddard was taking the next step, moving from theory to practice. Goddard had been fascinated by space travel since childhood, inspired by reading H.G. Wells's science fiction novel, The War of the Worlds. As a young man, he committed himself to making the dream of space travel a reality. Goddard understood that liquid propellants were the key to achieving the performance needed for space travel. Unlike solid fuels, which burn uncontrollably once ignited, liquid propellants could be fed into a combustion chamber at a controlled rate, allowing the engine to be throttled and shut down. The exhaust velocities achievable with liquid propellants were also significantly higher than those of solid fuels. On March 16, 1926, in a snow-covered field in Auburn, Massachusetts, Goddard achieved what no one had done before. He launched the world's first liquid-fueled rocket. The device was small, rising only 41 feet and flying for just 2.5 seconds. But it was a beginning, proof that liquid-fueled rockets could work. Over the following years, Goddard continued his experiments, moving to the desert of New Mexico, where he could work in greater secrecy and safety. His rockets grew larger and more sophisticated. He developed gyroscopic stabilization systems, fuel pumps, and other technologies that would prove essential for later rocket development. Yet Goddard worked in isolation, secretive and suspicious of others who might steal his ideas. He published little and shared less. When he died in 1945, his work was largely unknown outside a small circle. It would take decades for his contributions to be fully recognized. In Germany, a third pioneer was pursuing similar dreams. Hermann Oberth, born in Transylvania in 1894, became obsessed with space travel after reading Jules Verne's novels as a boy. He studied physics and mathematics, developing his own theories of rocket propulsion independently of Tsiolkovsky, whose work was unknown in the West. Oberth's 1923 book, The Rocket into Planetary Space, was a sensation in Germany. Written in accessible language, it captured the imagination of a generation and inspired the formation of rocket societies dedicated to making space travel a reality. The most important of these was the Verein für Raumschifffahrt, the Society for Space Travel, founded in Germany in 1927. Its members included engineers, scientists, and enthusiasts who built and tested small rockets, learning through trial and error the practical challenges of rocket propulsion. Among the young members of this society was a teenager named Werner von Braun. Born into an aristocratic family in 1912, von Braun had become fascinated with space travel after reading Oberth's book. He joined the Rocket Society while still a student and quickly demonstrated exceptional talent for both the technical and organizational aspects of rocket development. The German rocket enthusiasts dreamed of reaching the stars, but their work attracted the attention of a very different kind of organisation. The German military, forbidden by the Treaty of Versailles from developing conventional artillery, saw rockets as a potential loophole. Rockets were not specifically prohibited, and they might provide a new kind of long-range weapon. In 1932, the German army began funding rocket research. Von Braun, still in his early 20s, became the technical director of this military program. The dreamers of space travel had made a bargain that would haunt them for the rest of their lives. The military rocket program moved to a remote site on the Baltic coast called Peenemünde. There, with virtually unlimited resources and thousands of workers, von Braun and his team developed the most advanced rockets the world had ever seen. The culmination of their work was the A4, better known by its propaganda name, the V2. This was a quantum leap beyond anything that had come before. Standing 46 feet tall and weighing nearly 28,000 pounds at launch, the V2 was powered by a liquid-fueled engine burning alcohol and liquid oxygen. It could carry a 1-ton warhead more than 200 miles, reaching altitudes above 50 miles, crossing the boundary of space itself. The V2 was a technological marvel and a moral catastrophe. Its production relied on slave labour from concentration camps, with thousands of prisoners dying in the underground factories where the rockets were built. More people died making V2s than were killed by their warheads. When the V2s began falling on London and Antwerp in 1944, they brought terror but little military effect. They were too inaccurate and too expensive to be decisive weapons. But they demonstrated that rockets could reach unprecedented speeds and altitudes, that the technology for space travel was no longer merely theoretical. As World War II drew to a close, both American and Soviet forces raced to capture German rocket technology and the engineers who had created it. Von Braun and most of his senior team surrendered to the Americans, correctly calculating that their chances of continuing rocket work would be better in the West. Operation Paperclip brought von Braun and about 1,600 other German scientists and engineers to the United States. Their past was quietly overlooked in the interest of gaining their expertise. Similar efforts by the Soviet Union captured other German rocket specialists, and more importantly, complete V2 rockets and manufacturing equipment. The post-war years saw both superpowers developing their rocket capabilities, initially for military purposes. The V2 technology was studied, copied, and improved upon. New rockets were designed with ever greater range and payload capacity. The driving force was the Cold War. The United States and Soviet Union faced each other across an ideological divide, each convinced that the other posed an existential threat. Nuclear weapons had made war between the superpowers unthinkably destructive, but the means of delivering those weapons became a crucial area of competition. Intercontinental ballistic missiles, rockets capable of carrying nuclear warheads from one continent to another, became the ultimate strategic weapons. Both nations poured enormous resources into developing these missiles, creating in the process the technology that would make space exploration possible. In the Soviet Union, the rocket program was led by Sergei Korolev, a brilliant engineer who had survived the Stalinist purges and years in the Gulag labor camps. Korolev was driven by the same dream that had motivated Tsiolkovsky, Goddard, and von Braun, the dream of reaching space. But he operated in a system where military applications took priority, where secrecy was paramount, and where failure could mean imprisonment or death. Despite these constraints, Korolev achieved remarkable things. His R-7 rocket, developed as an intercontinental ballistic missile, was far more powerful than any American rocket of the time. It could lift heavy payloads into orbit, making it suitable not just for weapons delivery but for space exploration. In the United States, the rocket program was more fragmented. The Army, Navy, and Air Force all had separate missile programs, competing for funding and prestige. Von Braun and his team, now working for the Army at Huntsville, Alabama, had developed the Redstone missile and were eager to use it for space launches. But bureaucratic rivalries and policy decisions kept them on the sidelines. The stage was set for the event that would shock the world and transform space exploration from a dream into a race. On October 4, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite to orbit Earth. This small sphere, just 23 inches in diameter and weighing 184 pounds, carried only a simple radio transmitter. But its steady beeping, picked up by radio operators around the world, announced a new era in human history. The reaction in the United States was one of shock and fear. The same rocket that had placed Sputnik in orbit could deliver a nuclear warhead to American cities. The Soviets had demonstrated a technological capability that the United States could not match. The implications for national security and national prestige were profound. The American response was initially chaotic. The Naval Research Laboratory's Vanguard program, which had been designated to launch America's first satellite, suffered a humiliating failure when its rocket exploded on the launch pad in December 1957. Television cameras captured the disaster, broadcasting American failure to the world. Finally, the Army and von Braun's team were given the go-ahead. On January 31, 1958, a Jupiter-C rocket successfully placed Explorer 1 into orbit. America was in space, though clearly playing catch-up to the Soviets. Explorer 1 carried scientific instruments designed by James Van Allen of the University of Iowa. These instruments detected belts of radiation trapped by Earth's magnetic field, the first major scientific discovery of the space age. The Van Allen belts, as they came to be known, demonstrated that space exploration could yield knowledge as well as prestige. The space race had begun in earnest. Both superpowers poured resources into their space programs, each seeking to achieve firsts that would demonstrate technological superiority. The competition would drive both nations to accomplish things that might have taken decades in peacetime. The Soviets continued to rack up achievements. In November 1957, they launched Sputnik 2, carrying the dog Laika, the first living creature to orbit Earth. Though Laika died within hours due to overheating, a fact concealed by Soviet authorities for decades, the mission demonstrated that living beings could survive launch and at least brief exposure to the space environment. Luna 2 became the first human-made object to reach another celestial body when it impacted the Moon in September 1959. Luna 3, launched the following month, sent back the first photographs of the Moon's far side, revealing a landscape surprisingly different from the familiar near side. Each Soviet achievement spurred American efforts and deepened American anxiety. The United States created NASA, the National Aeronautics and Space Administration, in 1958 to coordinate civilian space activities. The new agency inherited various research programs and began planning ambitious missions. But the most important question was whether humans could survive in space. All the satellites and probes were merely precursors to the ultimate goal, sending people beyond Earth's atmosphere. Both nations began selecting and training their first astronauts and cosmonauts. In the United States, the Mercury program sought military test pilots with the right combination of skills, experience, and psychological stability. The 7 men selected, the Mercury 7, became instant celebrities, symbols of American courage and technological ambition. In the Soviet Union, the selection process was equally rigorous but more secretive. The cosmonauts were drawn from military pilots, chosen for their physical fitness, technical skills, and political reliability. Their identities were kept secret until after their missions. The Soviets won the race to put a human in space. On April 12, 1961, Yuri Gagarin became the first person to orbit Earth. His Vostok spacecraft completed a single orbit in 108 minutes, reaching an altitude of 203 miles. Gagarin, a 27-year-old fighter pilot with a winning smile, became an instant global celebrity and a powerful symbol of Soviet achievement. The American response came just 3 weeks later, when Alan Shepard became the first American in space. His flight was suborbital, a 15-minute arc that reached an altitude of 116 miles before splashing down in the Atlantic. It was a modest achievement compared to Gagarin's orbital flight, but it demonstrated that America was still in the race. President John F. Kennedy, inaugurated just months before Gagarin's flight, faced a decision about how to respond to the Soviet challenge. The options ranged from accepting second place in space to committing massive resources to catching up and surpassing the Soviets. Kennedy chose the boldest option. On May 25, 1961, he addressed a joint session of Congress and declared a goal that stunned the world. "I believe that this nation should commit itself to achieving the goal before this decade is out, of landing a man on the moon and returning him safely to the Earth." This was an audacious commitment. The United States had exactly 15 minutes of human spaceflight experience. The technology needed to reach the moon did not exist. The cost would be enormous. But Kennedy understood that the space race was about more than science or exploration. It was about demonstrating to the world which system, democracy or communism, could achieve greater things. The moon race had begun. The Mercury program continued through 1963 with increasingly ambitious missions. John Glenn became the first American to orbit Earth in February 1962, circling the planet 3 times in his Friendship 7 capsule. Technical problems during the flight, including a potentially faulty heat shield indicator, added drama to the mission and made Glenn a national hero. Subsequent Mercury flights extended the duration of American missions and tested various spacecraft systems. Scott Carpenter, Wally Schirra, and Gordon Cooper each flew orbital missions, with Cooper's May 1963 flight lasting more than 34 hours. The Soviets continued their own program, achieving additional firsts. German Titov spent more than a day in orbit in August 1961, becoming the first person to sleep in space and the first to experience space sickness. In August 1962, the Soviets launched 2 spacecraft simultaneously, Vostok 3 and Vostok 4, which came within a few miles of each other in orbit, though they could not maneuver to actually rendezvous. The most dramatic Soviet achievement of this period came in June 1963, when Valentina Tereshkova became the first woman in space. Her Vostok 6 mission lasted nearly 3 days, during which she orbited Earth 48 times. Tereshkova was not a pilot, but a textile worker, an amateur parachutist, selected partly for her proletarian background, which fit the Soviet narrative of space travel being accessible to ordinary workers. It would be 2 decades before another woman flew in space, and nearly 2 decades after that before an American woman reached orbit. Tereshkova's flight was a propaganda triumph for the Soviet Union, but it did not lead to any sustained effort to include women in the cosmonaut corps. The next major milestone was the first spacewalk, the first time a human being would leave the relative safety of a spacecraft and float freely in the vacuum of space. This was a necessary step toward the moon, where astronauts would need to work outside their spacecraft on the lunar surface. The Soviets achieved this first as well. On March 18, 1965, Alexei Leonov emerged from his Voskhod 2 spacecraft and spent about 12 minutes floating in space, connected to the spacecraft by a tether. The experience was nearly fatal. Leonov's spacesuit ballooned in the vacuum, making it impossible for him to re-enter the airlock. He had to partially deflate his suit, risking decompression sickness to squeeze back inside. The problems did not end there. The spacecraft's automatic re-entry system failed, forcing the crew to land manually. They came down in a remote forest in the Ural Mountains, where they spent a freezing night surrounded by wolves before rescue teams reached them. None of these difficulties were revealed publicly at the time. The American response came just 3 months later, when Ed White performed the first American spacewalk during the Gemini 4 mission. White spent 23 minutes outside the spacecraft, using a handheld maneuvering unit to move around. He was so exhilarated by the experience that he had to be ordered back inside when his oxygen supply ran low. "This is the saddest moment of my life," he said, as he reluctantly returned to the capsule. The Gemini program was America's bridge between Mercury and Apollo. Where Mercury had been about proving that Americans could survive in space, Gemini was about developing the skills and techniques needed to reach the moon. The program flew 10 crewed missions between 1965 and 1966, each one testing critical capabilities. Gemini 4 demonstrated spacewalking. Gemini 5 proved that astronauts could survive in space for the 8 days a lunar mission would require. Gemini 6 and 7 achieved the first space rendezvous, maneuvering to within a foot of each other in orbit. Gemini 8, flown by Neil Armstrong and David Scott, achieved the first docking between two spacecraft, linking up with an unmanned Agena target vehicle. The mission nearly ended in disaster when a stuck thruster sent the docked spacecraft into a violent spin. Armstrong's cool-headed response, undocking and using the re-entry thrusters to stabilize the spacecraft, saved the mission and the crew. Subsequent Gemini missions refined docking techniques, practiced spacewalking, and tested various systems and procedures. By the end of the program, American astronauts had accumulated far more spaceflight experience than their Soviet counterparts, and the techniques needed for a lunar mission had been proven. The Soviets, meanwhile, were falling behind. Their space program was plagued by bureaucratic infighting, funding shortages, and the death of Sergei Korolev in January 1966. Korolev had been the driving force behind Soviet space achievements, and his loss was devastating. The Soviet lunar program continued, but it would never recover its early momentum. While the crewed programs garnered the most public attention, both nations were also sending robotic spacecraft to the moon. These probes would scout the lunar surface, testing potential landing sites and returning crucial data about conditions astronauts would face. The American Ranger program sent spacecraft to crash into the moon while transmitting close-up photographs. After 6 failures, Rangers 7, 8 and 9 successfully returned thousands of images, revealing a surface covered with craters at all scales. The Surveyor program soft-landed spacecraft on the moon, demonstrating that the surface could support a landed spacecraft and returning detailed photographs and soil analysis. The Lunar Orbiter program mapped the moon from orbit, identifying potential Apollo landing sites. The Soviets achieved the first soft landing on the moon with Luna 9 in February 1966, returning the first photographs from the lunar surface. Luna 10 became the first spacecraft to orbit the moon 2 months later. All of this work was building toward the ultimate goal, landing humans on the moon. But the path to that achievement would be marked by tragedy as well as triumph. On January 27, 1967, astronauts Gus Grissom, Ed White, and Roger Chaffee were conducting a routine test of their Apollo 1 spacecraft at Cape Kennedy. The spacecraft was filled with pure oxygen at slightly above atmospheric pressure. When a spark ignited the oxygen-rich atmosphere, fire swept through the cabin with terrifying speed. All 3 astronauts died within seconds. The Apollo 1 fire was a devastating blow to the American space program. It revealed serious problems with spacecraft design and safety procedures that had been overlooked in the rush to meet Kennedy's deadline. The investigation that followed led to extensive redesigns of the spacecraft, including a new hatch that could be opened quickly from inside, a switch from pure oxygen to a mixed atmosphere at launch, and replacement of flammable materials throughout the cabin. The tragedy also brought a moment of reflection. 3 brave men had given their lives in the pursuit of a dream. Their sacrifice reminded everyone involved that space exploration was not a game or a propaganda exercise. It was a deadly serious endeavour where mistakes could be fatal. The Soviet program suffered its own tragedy just 3 months later. Vladimir Komarov launched aboard Soyuz 1 in April 1967 on a mission plagued by problems from the start. The spacecraft's solar panels failed to deploy properly, leaving it short of electrical power. When Komarov attempted to return to Earth, the parachute system malfunctioned. The main parachute failed to open, and the reserve chute became tangled. Soyuz 1 slammed into the ground at high speed, killing Komarov instantly. Komarov became the first person to die during a spaceflight. Like the Apollo 1 astronauts, he was a victim of schedule pressure and technical problems that had not been adequately addressed. Both tragedies led to lengthy pauses in their respective programs, while engineers worked to fix the problems that had been revealed. The American program resumed with Apollo 7 in October 1968, the first crewed flight of the Apollo spacecraft. Commander Wally Schirra and his crew spent 11 days in Earth orbit, testing the spacecraft systems and proving that the redesigned command module was safe and functional. The mission was a success, though Schirra's cranky interactions with mission control, exacerbated by a head cold, became legendary. The next mission would be one of the boldest in the history of exploration. Chapter 7. Apollo, humanity's greatest adventure. Apollo 8 was originally planned as a test of the lunar module in Earth orbit. But the lunar module was not ready, and intelligence suggested the Soviets might be planning a crewed flight around the moon. NASA made a daring decision. Apollo 8 would go to the moon without the lunar module, becoming the first crewed spacecraft to leave Earth orbit and travel to another world. On December 21, 1968, astronauts Frank Borman, Jim Lovell, and Bill Anders launched atop a Saturn V rocket, the most powerful machine ever built. The Saturn V stood 363 feet tall and generated 7.5 million pounds of thrust at liftoff. It was the creation of Wernher von Braun and his team, the culmination of decades of rocket development. The journey to the moon took 3 days. As Apollo 8 approached its destination, the astronauts became the first humans to see the far side of the moon with their own eyes. They fired their engine to enter lunar orbit, becoming the first humans to orbit another world. On Christmas Eve 1968, the crew of Apollo 8 broadcast a message to Earth. As images of the lunar surface scrolled across television screens around the world, the astronauts took turns reading from the Book of Genesis. In the beginning, God created the heaven and the earth. It was a moment of profound beauty and reflection, a reminder of the deeper meanings that space exploration could hold. But the most iconic image from Apollo 8 was not planned. As the spacecraft came around the moon's limb, Bill Anders looked out the window and saw something no human had ever seen before. Earth was rising above the lunar horizon, a brilliant blue and white marble against the black void of space. Anders grabbed his camera and captured the image that would become known as Earthrise. That photograph changed how humanity saw itself. For the first time, we could see our planet as a whole, a fragile oasis of life in an infinite darkness. The image became a symbol of the environmental movement and a reminder of our shared humanity. We were all passengers on that small blue spacecraft, travelling together through the cosmos. Apollo 8 returned safely to Earth, splashing down in the Pacific Ocean on December 27th. The mission had accomplished everything it set out to do and more. The path to the lunar landing was clear. Apollo 9 tested the lunar module in Earth orbit, practicing the rendezvous and docking procedures that would be essential for the landing mission. Apollo 10 went all the way to the Moon, testing the lunar module in lunar orbit and descending to within 9 miles of the surface. Everything worked as planned. The stage was set for Apollo 11. The crew selected for the first lunar landing attempt was Neil Armstrong, Buzz Aldrin, and Michael Collins. Armstrong, the commander, was a civilian test pilot known for his cool demeanour under pressure. Aldrin, the lunar module pilot, was a brilliant engineer with a doctorate from MIT. Collins, the command module pilot, would remain in lunar orbit while his crewmates descended to the surface. On July 16, 1969, Apollo 11 launched from Kennedy Space Center before an audience of millions. The Saturn V performed flawlessly, sending the spacecraft on its trajectory to the Moon. 3 days later, Apollo 11 entered lunar orbit. On July 20th, Armstrong and Aldrin entered the lunar module, named Eagle, and began their descent to the surface. Collins, alone in the command module Columbia, watched them go. He would spend the next day orbiting the Moon in solitude, out of radio contact with Earth for 48 minutes of each 2-hour orbit, the loneliest human being in history. The descent did not go smoothly. As Eagle approached the surface, program alarms began sounding in the cockpit. The onboard computer was being overloaded with data, threatening to abort the landing. In Houston, a young engineer named Steve Bales made a crucial call. The alarms were not critical. The landing could continue. Then Armstrong looked out the window and saw a problem. The computer was guiding them toward a boulder field, not a safe landing spot. With fuel running low, Armstrong took manual control and flew the lunar module like a helicopter, searching for a clear area. The fuel gauge dropped toward empty, 60 seconds of fuel remaining, 30 seconds. Contact light. A probe dangling beneath the lunar module's foot pads touched the surface. Armstrong shut down the engine. Eagle settled onto the Moon, with about 25 seconds of fuel to spare. Houston Tranquility Base here. The Eagle has landed. In mission control, and in living rooms around the world, people erupted in cheers and tears. Humanity had reached another world. 6.5 hours later, Neil Armstrong opened the hatch of the lunar module and began climbing down the ladder. A television camera mounted on the spacecraft transmitted grainy black and white images to an estimated 600 million people watching on Earth, the largest television audience in history up to that time. Armstrong reached the bottom of the ladder and paused. He was about to become the first human being to set foot on another world. The moment called for words that would be remembered for all time. That's one small step for man, one giant leap for mankind. Armstrong stepped off the footpad and onto the lunar surface. He was standing in the Sea of Tranquility, a vast plain of ancient lava covered with a layer of fine grey dust. The sky above was black, the sun blazing without the softening effect of an atmosphere. In the distance, the horizon curved noticeably, a reminder of how small the Moon is compared to Earth. Buzz Aldrin joined Armstrong on the surface about 20 minutes later. "Beautiful view," he said, as he looked around at the stark lunar landscape. "Magnificent desolation." The two astronauts spent about 2.5 hours outside the lunar module. They planted an American flag, though the lack of wind meant it had to be held out by a horizontal rod. They set up scientific instruments, including a seismometer to detect moonquakes and a reflector that would allow precise measurements of the Earth-Moon distance using laser beams. They collected samples of lunar soil and rocks, 45 pounds of material that would be studied by scientists for decades, and they took photographs documenting their activities and the alien landscape around them. Throughout their moonwalk, Armstrong and Aldrin received a phone call from President Richard Nixon, who told them, for one priceless moment in the whole history of man, all the people on this earth are truly one. It was perhaps the only time in human history when that statement was close to being true. People around the world, regardless of nationality or ideology, shared in the wonder of the moment. Even in the Soviet Union, state television broadcast the landing, acknowledging the American achievement. After their surface activities were complete, Armstrong and Aldrin returned to the lunar module and prepared for the most critical phase of the mission, the ascent from the lunar surface. If the ascent engine failed to ignite, they would be stranded on the moon with no hope of rescue. The engine fired perfectly. Eagle rose from the surface, leaving behind its descent stage and the lower half of the spacecraft. The astronauts rendezvoused with Collins in the command module, transferred their samples and equipment, and jettisoned the lunar module. On July 24th, Apollo 11 splashed down in the Pacific Ocean. The crew was recovered by the aircraft carrier USS Hornet and placed in quarantine, a precaution against the possibility of lunar microbes. After 17 days of isolation, they were released to a hero's welcome. The Apollo 11 mission was a triumph of human ingenuity, courage, and determination. It fulfilled Kennedy's challenge and demonstrated what humanity could achieve when united in a common purpose. But it was only the beginning of lunar exploration. Apollo 12 launched in November 1969, just 4 months after Apollo 11. The mission demonstrated precision landing capability, touching down within walking distance of the Surveyor 3 probe that had landed 2.5 years earlier. Astronauts Pete Conrad and Alan Bean retrieved parts from the Surveyor, providing valuable data on how materials survived long-term exposure to the lunar environment. Apollo 13 launched in April 1970, intended to land in the Fra Mauro Highlands. But 56 hours into the mission, an oxygen tank in the service module exploded, crippling the spacecraft. The crew, Jim Lovell, Jack Swigert, and Fred Hayes, faced a desperate situation. They were more than 200,000 miles from Earth, their spacecraft damaged and leaking oxygen. "Houston, we've had a problem." Those words began one of the most dramatic rescue operations in history. The lunar landing was immediately aborted. The crew moved into the lunar module, using it as a lifeboat. Mission controllers in Houston worked around the clock to devise procedures for conserving power, managing carbon dioxide levels, and navigating the crippled spacecraft back to Earth. The crew swung around the moon, using its gravity to send them back toward Earth. They endured freezing temperatures as power was conserved for the critical re-entry. They faced the challenge of carbon dioxide buildup as the lunar module's scrubbers became saturated. Engineers on the ground devised a way to adapt command module scrubbers to work in the lunar module, using only materials available on board. After 4 harrowing days, Apollo 13 re-entered Earth's atmosphere and splashed down safely in the Pacific. The mission was deemed a successful failure, a disaster that had been averted through ingenuity, teamwork, and courage. It demonstrated that NASA could handle emergencies and reinforced the importance of thorough preparation and flexible problem-solving. Apollo 14 returned to the Fra Mauro site in February 1971, completing the mission that Apollo 13 had been unable to finish. Commander Alan Shepard, the first American in space, became the oldest person to walk on the moon at age 47. In a moment of levity, Shepard hit 2 golf balls on the lunar surface, claiming they went miles and miles and miles in the low gravity. The final 3 Apollo missions, 15, 16 and 17, were extended scientific expeditions. They carried the Lunar Roving Vehicle, an electric car that allowed astronauts to travel miles from the landing site and explore a much larger area. They spent more time on the surface and brought back larger quantities of samples. Apollo 15 landed near Hadley Ryle, a winding canyon that provided access to ancient lunar geology. Astronauts David Scott and James Irwin drove their rover to the edge of the Ryle and collected samples that revealed the moon's volcanic history. Apollo 16 explored the lunar highlands, the ancient, heavily cratered terrain that makes up most of the moon's surface. John Young and Charles Duke collected samples that helped scientists understand the moon's early history and the intense bombardment it experienced billions of years ago. Apollo 17, in December 1972, was the final Apollo mission. Commander Eugene Cernan and lunar module pilot Harrison Schmitt, the only scientist to walk on the moon, spent 3 days on the surface, the longest stay of any Apollo mission. They drove their rover more than 22 miles and collected 243 pounds of samples. As Cernan prepared to climb the ladder for the last time, he paused to speak. As I take man's last step from the surface, back home for some time to come, but we believe not too long into the future, I'd like to just say what I believe history will record, that America's challenge of today has forged man's destiny of tomorrow. He was wrong about one thing. More than 50 years later, no human being has returned to the moon. The footprints left by the Apollo astronauts remain undisturbed, preserved in the airless lunar environment. The Apollo program had achieved its goal of landing humans on the moon and returning them safely to Earth. 12 astronauts walked on the lunar surface, spending a total of about 80 hours outside their spacecraft. They brought back 842 pounds of lunar samples that continue to be studied today. But the program was about more than flags and footprints. The scientific instruments left on the moon continued to return data for years. The samples revealed the moon's history, showing that it formed from debris ejected when a Mars-sized object collided with the early Earth. The technology developed for Apollo advanced fields from computing to materials science. Perhaps most importantly, Apollo changed how we see ourselves. The images of Earth from space, small and fragile, against the infinite blackness, inspired a new awareness of our planet's vulnerability. The achievement of reaching the moon demonstrated what humanity could accomplish when we set aside our differences and work toward a common goal. The Apollo program cost about $25 billion, equivalent to roughly $150 billion in today's currency. At its peak, it employed 400,000 people and consumed more than 4% of the federal budget. It was the largest peacetime mobilization of resources in American history. Was it worth it? The answer depends on what you value. If space exploration is merely about practical benefits, then Apollo's return on investment is debatable. If it is about pushing the boundaries of human capability, about inspiring future generations, about taking our first steps toward becoming a spacefaring species, then Apollo was priceless. The end of Apollo did not mean the end of human spaceflight. Even as the last astronauts were walking on the moon, new programs were taking shape that would define the next era of space exploration. Chapter 8. Space Stations and the Shuttle Era. The idea of a space station, a permanent outpost in orbit where humans could live and work for extended periods, had been part of space visionaries' dreams since the early 20th century. Tsiolkovsky, Oberth, and von Braun had all written about space stations as essential stepping stones to deeper space exploration. The first space stations were built not by the United States, but by the Soviet Union. With their lunar program in shambles after multiple failures of their giant N-1 rocket, Soviet planners redirected their efforts toward Earth orbit. The Salyut program would give them new achievements to celebrate and valuable experience in long-duration spaceflight. Salyut 1 launched in April 1971, becoming the world's first space station. It was a cylinder about 65 feet long and 13 feet in diameter, with living quarters, work areas, and scientific equipment. The first crew to visit, aboard Soyuz 10, was unable to enter due to a docking problem. The second crew, aboard Soyuz 11, successfully docked and spent 23 days aboard the station, setting a new spaceflight duration record. But tragedy struck during their return to Earth. A valve in the Soyuz spacecraft opened during re-entry preparations, venting the cabin atmosphere into space. Cosmonauts Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev died of asphyxiation before they could close the valve. They were not wearing spacesuits, a decision that had been made to save weight and space. The deaths of the Soyuz 11 crew led to redesigns of the Soyuz spacecraft, including the requirement that crews wear spacesuits during launch and re-entry. These changes reduced the spacecraft's capacity from 3 to 2 cosmonauts, but significantly improved safety. The Salyut program continued through the 1970s and into the 1980s, with a series of stations that grew increasingly sophisticated. Some were military reconnaissance platforms, equipped with cameras and other sensors. Others were civilian scientific stations, where cosmonauts conducted experiments in materials science, Earth observation, and biology. The longest-serving Salyut station was Salyut 7, which operated from 1982 to 1986. It hosted 10 crews and set new records for spaceflight duration. Cosmonauts learned to live and work in space for months at a time, developing techniques for maintaining physical health in weightlessness and managing the psychological challenges of long-duration spaceflight. The United States launched its own space station in 1973. Skylab was built from hardware originally developed for the Apollo program, including a converted Saturn V third stage that served as the main living and working area. It was much larger than the Salyut stations, with about 12,000 cubic feet of habitable volume. Skylab's launch was nearly a disaster. During ascent, a micrometeoroid shield tore away, taking one of the station's solar panels with it and jamming the other. The station reached orbit but was overheating and short of electrical power. The first crew, launched 11 days later, carried tools and materials for repairs. In a series of spacewalks, they deployed a sunshade to cool the station and freed the jammed solar panel. Their ingenuity saved the station and demonstrated the value of having humans in space to handle unexpected problems. 3 crews visited Skylab over the following year, spending 28, 59, and 84 days in orbit respectively. They conducted hundreds of experiments in solar astronomy, Earth observation, materials science, and human physiology. They proved that humans could live and work productively in space for extended periods. Skylab was abandoned after the third crew departed in February 1974. Plans to boost its orbit using the space shuttle were delayed when the shuttle program fell behind schedule. In 1979, Skylab's orbit decayed, and the station re-entered the atmosphere, scattering debris across the Indian Ocean and Western Australia. The mid-1970s saw a brief thaw in Cold War tensions that extended to space. The Apollo-Soyuz test project, launched in July 1975, was the first international crewed space mission. An American Apollo spacecraft and a Soviet Soyuz spacecraft rendezvoused and docked in orbit, and their crews visited each other's spacecraft, shaking hands through the connecting tunnel. The mission was largely symbolic, a demonstration that former rivals could cooperate in space. It would be another 2 decades before such cooperation became routine, but Apollo-Soyuz showed that it was possible. The space shuttle was intended to revolutionize space travel. Unlike previous spacecraft, which were used once and discarded, the shuttle would be reusable. It would launch like a rocket, operate in space like a spacecraft, and land like an airplane. NASA promised it would fly frequently and cheaply, making space access routine. The shuttle consisted of 3 main components. The orbiter was a delta-winged spacecraft about the size of a small airliner, with a crew cabin, a large cargo bay, and 3 main engines. The external tank, the large orange cylinder that dominated launch images, held the liquid hydrogen and liquid oxygen that fed the main engines. 2 solid rocket boosters provided most of the thrust during the first 2 minutes of flight. Development of the shuttle took longer and cost more than expected. The first orbital flight, STS-1, did not occur until April 1981, more than a decade after the program began. Astronauts John Young and Robert Crippen piloted Columbia on a 2-day mission that tested the spacecraft's systems and proved it could reach orbit and return safely. The shuttle fleet eventually grew to include 4 orbiters: Columbia, Challenger, Discovery, and Atlantis. A 5th orbiter, Enterprise, was built for atmospheric test flights, but never flew in space. Each orbiter was designed to fly up to 100 missions. Throughout the 1980s, the shuttle flew increasingly ambitious missions. It deployed satellites, including communication satellites and scientific spacecraft. It carried Spacelab, a laboratory module built by the European Space Agency, in its cargo bay. It retrieved and repaired satellites in orbit, demonstrating capabilities no other spacecraft possessed. The shuttle also carried the first American woman into space. Sally Ride launched aboard Challenger in June 1983, more than 2 decades after Valentina Tereshkova's flight. Ride was a physicist who had been selected as an astronaut in 1978, part of the first class to include women. She flew again in 1984 and later served on the commissions investigating both shuttle disasters. The shuttle program suffered its first tragedy on January 28, 1986. Challenger launched on a cold Florida morning, with temperatures near freezing. 73 seconds after liftoff, the spacecraft broke apart, killing all 7 crew members. The cause was a failure of an O-ring seal in one of the solid rocket boosters. The cold temperatures had stiffened the rubber O-rings, preventing them from sealing properly. Hot gases burned through the joint and ignited the external tank, destroying the vehicle. Among the crew was Krista McAuliffe, a high school teacher who'd been selected to be the first private citizen in space. Her presence had generated enormous public interest in the mission, and millions of schoolchildren watched the launch live. The disaster was a national trauma. The investigation that followed revealed serious problems with NASA's safety culture. Engineers had warned about the O-ring problem before the launch, but their concerns had been overruled by managers under pressure to maintain the launch schedule. The Rogers Commission, which investigated the disaster, called for significant changes in how NASA managed risk. The shuttle program was grounded for nearly 3 years, while modifications were made and procedures were revised. Flights resumed in September 1988 with the launch of Discovery. The program continued through the 1990s, though the promised frequency and low cost never materialized. While the shuttle program was recovering from Challenger, the Soviet Union was building something remarkable: Mir, which means both peace and world in Russian, was a modular space station that would grow over time as new components were added. The core module launched in February 1986. Over the following decade, additional modules were added, expanding the station's capabilities and living space. At its peak, Mir had 6 modules with about 15,000 cubic feet of habitable volume. Mir hosted crews almost continuously from 1987 to 1999. Cosmonauts set new records for long-duration spaceflight, with Valery Polyakov spending 437 consecutive days in orbit, a record that still stands. The station served as a laboratory for studying the effects of long-term spaceflight on the human body and for conducting experiments in materials science, biology, and Earth observation. Mir also became a symbol of international cooperation. After the Cold War ended, the United States and Russia began collaborating in space. American astronauts visited Mir aboard the space shuttle, and later American astronauts lived aboard the station for months at a time as part of the Shuttle Mir program. This cooperation was not always smooth. Mir was aging and increasingly prone to problems. A fire broke out in 1997, filling the station with smoke. A few months later, a Progress cargo ship collided with the station during a manual docking test, puncturing one of the modules and causing a partial depressurization. Despite these challenges, the Shuttle Mir program provided valuable experience in international space cooperation and long-duration spaceflight. It laid the groundwork for an even more ambitious project that was already taking shape. The Space Shuttle suffered its second disaster on February 1st, 2003. Columbia was returning from a 16-day scientific mission when it broke apart during re-entry, killing all 7 crew members. The cause was traced to a piece of foam insulation that had broken off the external tank during launch and struck the leading edge of the orbiter's left wing. The impact created a hole in the reinforced carbon-carbon panels that protected the wing from re-entry heating. When Columbia entered the atmosphere, superheated gases penetrated the wing structure, causing it to fail. The Columbia Accident Investigation Board found that the foam strike had been observed during the mission, but NASA managers had dismissed concerns about potential damage. The board's report criticized NASA's safety culture, finding that many of the organizational problems identified after Challenger had resurfaced. The shuttle program was again grounded, this time for more than 2 years. When flights resumed, new procedures were implemented to inspect the orbiter in space and repair any damage. The program continued until 2011, when the final shuttle mission, STS-135, brought the program to an end. Over 30 years, the Space Shuttle flew 135 missions. It deployed satellites, serviced the Hubble Space Telescope, and carried most of the components of the International Space Station into orbit. But it never achieved the routine, low-cost access to space that had been promised. Each mission cost hundreds of millions of dollars, and 14 astronauts lost their lives. The shuttle's legacy is mixed. It was an engineering marvel, a spacecraft unlike anything that had come before. It enabled missions that would have been impossible with any other vehicle, but it was also a compromise designed to meet too many competing requirements and never quite succeeding at any of them. Chapter 9: Robots Among the Planets. While human spaceflight captured the public imagination, robotic spacecraft were quietly revolutionizing our understanding of the solar system. These mechanical explorers traveled to places too distant or too dangerous for human visitors, sending back images and data that revealed worlds of astonishing diversity and beauty. The exploration of the inner solar system began in the early 1960s with the Mariner program. Mariner 2, launched in 1962, became the first spacecraft to successfully fly by another planet when it passed Venus in December of that year. It found a world very different from Earth, with surface temperatures hot enough to melt lead and a crushing atmosphere of carbon dioxide. Mariner 4 reached Mars in 1965, returning the first close-up images of the red planet. The photographs showed a cratered, apparently dead world, very different from the Mars of science fiction, with its canals and civilizations. Later Mariner missions revealed more of Mars's complexity, including enormous volcanoes and a canyon system that dwarfs anything on Earth. Mariner 10 visited both Venus and Mercury in 1974 and 1975, using Venus's gravity to bend its trajectory toward the innermost planets. It was the first spacecraft to use this gravity assist technique, which would become essential for missions to the outer solar system. Mariner 10 revealed Mercury as a heavily cratered world resembling the Moon, with extreme temperature variations between its sun-baked day side and frigid night side. The Soviet Union focused much of its planetary exploration on Venus, a world that seemed more hospitable before its true nature was understood. The Venera program sent a series of increasingly sophisticated spacecraft to our nearest planetary neighbour. Early Venera missions were crushed by Venus's atmosphere before reaching the surface, revealing just how extreme conditions there were. The atmospheric pressure at Venus's surface is about 90 times that of Earth, equivalent to being nearly a kilometre underwater. The temperature exceeds 850 degrees Fahrenheit, hot enough to melt lead. Venera 7 became the first spacecraft to successfully land on another planet and transmit data from the surface in December 1970. It survived for only 23 minutes before succumbing to the heat and pressure, but it confirmed the hellish conditions that had been inferred from earlier missions. Later, Venera landers were more robust and carried cameras. Venera 9 and 10 returned the first photographs from the surface of another planet in 1975, showing a rocky landscape beneath an orange sky. Venera 13 and 14 in 1982 returned colour photographs and even recorded the sound of wind on Venus. The Venera program demonstrated the Soviet Union's considerable expertise in planetary exploration, even as they fell behind in the human spaceflight race. The images from Venus's surface remain among the most remarkable achievements of the space age. The exploration of Mars accelerated in the 1970s with the Viking program, the most ambitious planetary mission yet attempted. Two identical spacecraft, each consisting of an orbiter and a lander, were sent to Mars with the goal of searching for signs of life. Viking 1 and Viking 2 arrived at Mars in 1976, with the landings timed to coincide with the American bicentennial celebration. The orbiters mapped the planet from above, while the landers studied the surface in unprecedented detail. The Viking landers were equipped with experiments designed to detect signs of life in the Martian soil. They scooped up samples and exposed them to nutrients, looking for signs of metabolic activity. They heated samples and analysed the gases released, searching for organic molecules. The results were puzzling. Some experiments showed reactions that might indicate biological activity, while others found no organic molecules at all. After decades of analysis, most scientists concluded that the results were caused by chemical reactions in the Martian soil rather than life. But the question remains open, and the search for life on Mars continues to this day. The Viking orbiters continued operating for years, mapping the Martian surface in detail and observing seasonal changes. They revealed a world with a complex geological history, including evidence of ancient water flows that suggested Mars might once have been more hospitable to life. The outer solar system presented even greater challenges. The giant planets, Jupiter, Saturn, Uranus, and Neptune, orbit at enormous distances from the Sun. Reaching them requires years of travel, and the spacecraft must operate far from the solar energy that powers most satellites. The Pioneer program sent the first spacecraft to the outer solar system. Pioneer 10, launched in 1972, became the first spacecraft to traverse the asteroid belt and fly by Jupiter. It returned the first close-up images of the giant planet and made the first direct observations of its intense radiation belts. Pioneer 11 followed a year later, flying by both Jupiter and Saturn. It passed through Saturn's ring plane, demonstrating that the rings were safe to navigate, and discovered a new moon and a new ring. Both Pioneer spacecraft carried plaques designed by Carl Sagan and Frank Drake, depicting a man and woman and providing information about Earth's location in the galaxy. These plaques were messages in a bottle, cast into the cosmic ocean in the hope that someday, somewhere, someone might find them. The Voyager program built on Pioneer's success with far more capable spacecraft. Voyager 1 and Voyager 2 launched in 1977, taking advantage of a rare alignment of the outer planets that occurs only once every 175 years. This alignment allowed a single spacecraft to visit multiple planets, using each one's gravity to bend its trajectory toward the next. Voyager 1 flew by Jupiter in 1979, returning images of unprecedented detail. It discovered active volcanoes on the moon Io, the first found anywhere beyond Earth. It revealed Europa's icy surface, cracked and fractured in patterns suggesting a liquid ocean beneath. It found that Jupiter's Great Red Spot was a storm larger than Earth, raging for centuries. Voyager 1 then flew by Saturn, passing close to the moon Titan. Titan's thick atmosphere, the only substantial atmosphere on any moon in the solar system, prevented the spacecraft from seeing the surface. But the encounter bent Voyager 1's trajectory out of the plane of the solar system, ending its planetary tour. Voyager 2 followed a different path. After visiting Jupiter and Saturn, it continued to Uranus, arriving in 1986. Uranus proved to be a strange world, tilted on its side so that its poles take turns pointing toward the sun. Its moon. Miranda showed a surface of chaotic terrain, as if the moon had been shattered and reassembled. Voyager 2's final planetary encounter was Neptune in 1989. The blue planet revealed itself as a dynamic world with the fastest winds in the solar system and a great dark spot similar to Jupiter's Great Red Spot. Its moon Triton, with geysers of nitrogen gas erupting from its surface, was clearly a captured Kuiper Belt object, a visitor from the outer reaches of the solar system. Both Voyager spacecraft continue to operate today, more than 4 decades after their launch. They have left the region of the planets and entered interstellar space, the first human-made objects to do so. They carry golden records containing sounds and images of Earth, a message to any intelligence that might someday encounter them. The exploration of the outer solar system continued with more specialized missions. Galileo, launched in 1989, became the first spacecraft to orbit Jupiter. It spent 8 years studying the giant planet and its moons, dropping a probe into Jupiter's atmosphere and making repeated close passes of the Galilean moons. Galileo's discoveries transformed our understanding of the Jovian system. It found strong evidence for a liquid water ocean beneath Europa's icy crust, making that moon one of the most promising places to search for life beyond Earth. It observed volcanic eruptions on Io and discovered that Ganymede has its own magnetic field. Cassini-Huygens, a joint mission of NASA and the European Space Agency, arrived at Saturn in 2004. It would spend 13 years exploring the ringed planet and its moons, one of the most successful planetary missions ever flown. Cassini revealed Saturn's rings in exquisite detail, showing their complex structure and dynamics. It discovered new moons and observed storms and weather patterns on Saturn itself. It made repeated close passes of Titan, using radar to peer through the moon's opaque atmosphere and reveal a world with lakes and seas of liquid methane. The Huygens probe, carried to Saturn by Cassini, descended through Titan's atmosphere in January 2005. It was the first landing in the outer solar system. Touching down on a surface littered with ice pebbles, rounded by flowing liquid, the images from Titan's surface showed a landscape eerily reminiscent of Earth, with river channels and shorelines, but composed of water ice and liquid hydrocarbons rather than rock and water. Cassini's mission ended in 2017 when the spacecraft was deliberately plunged into Saturn's atmosphere. This was done to prevent any possibility of the spacecraft eventually crashing into Enceladus or Titan, moons that might harbour life. The spacecraft transmitted data until the very end, providing unprecedented measurements of Saturn's atmosphere and magnetic field. The exploration of Mars has been particularly intensive, with a succession of orbiters, landers, and rovers building an increasingly detailed picture of the red planet. Mars Pathfinder landed in 1997, carrying a small rover named Sojourner. This was the first rover to operate on another planet, demonstrating that mobile exploration was possible. Sojourner was tiny, about the size of a microwave oven, but it proved the concept that would lead to much more capable successors. The Mars exploration rovers, Spirit and Opportunity, landed in January 2004 on opposite sides of the planet. Each rover was about the size of a golf cart, far larger and more capable than Sojourner. They were designed for 90-day missions but far exceeded all expectations. Spirit landed in Gusev Crater, a basin that scientists believed might once have held a lake. The rover explored for more than 6 years, climbing hills, examining rocks, and surviving dust storms that threatened to end its mission. Spirit finally fell silent in 2010 after becoming stuck in soft soil and losing the ability to position its solar panels toward the winter sun. Opportunity landed on the opposite side of Mars, in a region called Meridiani Planum. Almost immediately, it made a remarkable discovery. The rover had landed inside a small crater, and the walls of that crater exposed layers of sedimentary rock that could only have formed in the presence of liquid water. Mars had indeed once been a wetter world. Opportunity continued exploring for an astonishing 15 years, travelling more than 28 miles across the Martian surface. It examined countless rocks and craters, finding more evidence of ancient water and conditions that might once have been suitable for life. The rover finally fell silent in 2019 after a global dust storm blocked sunlight from its solar panels. The longevity of Spirit and Opportunity demonstrated the value of robust engineering and careful mission design. They also captured the public imagination in a way that few robotic missions had before. People followed their adventures, celebrated their discoveries, and mourned when they finally fell silent. These robots had become explorers that humanity could root for. Curiosity, the Mars Science Laboratory rover, landed in August 2012 using a daring new technique. The rover was too heavy for the airbag landing system used by previous missions, so engineers devised a sky crane that lowered the rover on cables from a hovering descent stage. It was an audacious approach that worked flawlessly. Curiosity is a mobile laboratory the size of a small car, equipped with instruments capable of analysing the composition of rocks and soil, detecting organic molecules, and measuring radiation levels. It landed in Gale Crater, which contains a mountain of layered sediments that record billions of years of Martian history. Over more than a decade of exploration, Curiosity has climbed the lower slopes of Mount Sharp, examining layer after layer of ancient rock. It has found organic molecules, the building blocks of life as we know it. It has detected seasonal variations in methane, a gas that on Earth is often produced by living organisms. It has measured radiation levels that help scientists understand the challenges future human explorers will face. Curiosity continues to operate today, still climbing Mount Sharp and still making discoveries. Its nuclear power source, which generates electricity from the decay of plutonium, gives it a lifespan measured in decades rather than years. Perseverance, the most recent Mars rover, landed in February 2021. It is similar in design to Curiosity, but carries different instruments focused on searching for signs of ancient life. It landed in Jezero Crater, which billions of years ago contained a lake fed by a river that carved a delta into the crater wall. Perseverance is doing something no previous mission has attempted. It is collecting samples of Martian rock and soil, sealing them in tubes and leaving them on the surface for a future mission to retrieve and return to Earth. These samples, when they finally reach terrestrial laboratories, will be studied with instruments far more sophisticated than any that could be sent to Mars. The rover also carried a small helicopter named Ingenuity. This was a technology demonstration, an attempt to prove that powered flight was possible in Mars's thin atmosphere. Ingenuity was designed for just 5 flights, but it far exceeded expectations, completing more than 70 flights before finally ending its mission in 2024. It scouted terrain for Perseverance and demonstrated that aerial exploration of Mars is feasible. The exploration of Mars has revealed a world that was once much more like Earth. Billions of years ago, Mars had a thicker atmosphere, liquid water on its surface, and possibly the conditions necessary for life to arise. Whether life ever did arise there remains one of the great unanswered questions of science. Other destinations in the solar system have also received attention from robotic explorers. The Dawn spacecraft visited the 2 largest objects in the asteroid belt, Vesta and Ceres, between 2011 and 2018. It found that Vesta is a dry, rocky world, while Ceres has water ice and organic molecules on its surface. New Horizons flew past Pluto in July 2015, providing the first close-up look at this distant world. Pluto proved to be far more complex and geologically active than anyone had expected. Its heart-shaped nitrogen ice plain, informally named Tombor Regio after Pluto's discoverer, showed no craters, indicating that geological processes have resurfaced it relatively recently. New Horizons continued into the Kuiper Belt, flying past a small object named Arakoth in 2019. This primitive body, shaped like a snowman, is a remnant from the formation of the solar system, preserved in the deep freeze of the outer solar system for billions of years. The Japanese Space Agency has conducted ambitious asteroid missions. Hayabusa visited asteroid Itokawa in 2005 and returned samples to Earth in 2010, despite numerous technical problems that nearly doomed the mission. Hayabusa 2 visited asteroid Ryugu, collecting samples and returning them to Earth in 2020. These samples are providing insights into the composition of primitive solar system bodies and the delivery of water and organic molecules to the early Earth. OSIRIS-REx, a NASA mission, visited asteroid Bennu and returned the largest asteroid sample ever collected in September 2023. The sample, weighing about 250 grams, is being analysed by scientists around the world, revealing the composition of a carbon-rich asteroid that may be similar to the bodies that delivered the building blocks of life to Earth. The robotic exploration of the solar system continues to accelerate. Missions currently operating or in development We'll visit Europa to search for signs of life in its subsurface ocean, return samples from Mars, explore Titan with a flying drone, and probe the atmospheres of the ice giants Uranus and Neptune. These robotic pioneers are our eyes and hands in the cosmos, extending human presence to places we cannot yet go ourselves. They have revealed a solar system of astonishing diversity, with worlds of fire and ice, of storms and silence, of ancient history and ongoing change. Each mission builds on those that came before, asking new questions and finding answers that raise still more questions. Chapter 10: The International Space Station Era. The end of the Cold War brought new possibilities for international cooperation in space. The rivalry that had driven the space race gave way to partnerships that would have been unthinkable just a few years earlier. The most ambitious of these partnerships was the International Space Station. The idea of a large, permanently crewed space station had been discussed for decades. The United States had planned a station called Freedom in the 1980s, but budget constraints and changing priorities had prevented its construction. Russia had extensive experience with space stations through the Salyut and Mir programs, but lacked the resources to build a next-generation station alone. In 1993, the United States and Russia agreed to merge their space station programs. They were joined by the European Space Agency, Japan and Canada, creating a partnership of 15 nations committed to building and operating the largest structure ever assembled in space. The International Space Station would be built from modules launched separately and connected in orbit. This modular approach allowed different partners to contribute components suited to their capabilities and interests. It also meant that construction would take many years, with the station growing piece by piece. The first component, the Russian Zarya module, launched in November 1998. 2 weeks later, the Space Shuttle Endeavour delivered the American Unity node, and astronauts connected the two modules during a series of spacewalks. The International Space Station had begun to take shape. Construction continued over the following years, with new modules, solar arrays, and other components added on successive missions. The Russian Zvezda service module, launched in 2000, provided living quarters and life support systems. The American Destiny Laboratory, installed in 2001, provided facilities for scientific research. The station has been continuously occupied since November 2000, when the first resident crew arrived. Expedition 1, consisting of American astronaut Bill Shepard and Russian cosmonauts Yuri Gidzenko and Sergei Krikalev, spent 4 months aboard the station, establishing the routines and procedures that would be followed by subsequent crews. The pace of construction accelerated after the Space Shuttle returned to flight following the Columbia disaster. The station's backbone truss, a structure more than 300 feet long, was assembled piece by piece. Massive solar arrays were deployed, providing electrical power for the growing station. Additional laboratory modules from Europe and Japan were added, expanding the station's research capabilities. The completed International Space Station is an engineering marvel. It spans an area larger than a football field and has a mass of nearly 1 million pounds. Its solar arrays generate enough electricity to power about 40 homes. Its pressurized volume, the space where crew members can live and work, is roughly equivalent to a Boeing 747. Life aboard the station follows a carefully planned routine. Crew members typically work about 10 hours a day, 6 days a week. Their tasks include conducting scientific experiments, maintaining station systems, and performing spacewalks for repairs and upgrades. Exercise is mandatory, with each crew member spending about 2 hours daily on specially designed equipment to combat the muscle and bone loss that occurs in weightlessness. The station has hosted more than 270 people from 21 countries. Crew members typically stay for about 6 months, though some have remained for nearly a year. The record for longest single spaceflight by an American is held by Mark Vande Hei, who spent 355 days aboard the station in 2021 and 2022. Scientific research on the International Space Station spans many disciplines. The microgravity environment allows experiments that would be impossible on Earth, where gravity affects everything from fluid behavior to crystal growth. Researchers have studied how flames burn in weightlessness, how plants grow without a consistent up and down, and how the human body adapts to life in space. Medical research has been particularly important. Understanding how the body responds to long-duration spaceflight is essential for planning future missions to Mars and beyond. Studies on the station have examined bone loss, muscle atrophy, fluid shifts, vision changes, and immune system function. The knowledge gained is helping scientists develop countermeasures to protect future deep space explorers. The station has also served as a testbed for technologies that will be needed for future exploration. Life support systems that recycle water and oxygen, advanced spacesuits, and robotic systems have all been tested and refined in the station's unique environment. Perhaps most importantly, the International Space Station has demonstrated that nations can work together on complex, long-term projects in space. Despite political tensions on Earth, the partnership has endured for more than 2 decades. Astronauts and cosmonauts live and work together, depending on each other for their survival. The station is a symbol of what humanity can achieve when we choose cooperation over competition. The station's future is now being planned. NASA has committed to operating the American segment through 2030, and discussions are ongoing about what comes next. Commercial space stations are being developed that may eventually replace the International Space Station, continuing the human presence in low Earth orbit while freeing government resources for exploration beyond. When the International Space Station eventually reaches the end of its operational life, it will be deorbited in a controlled manner, with most of the structure burning up in the atmosphere, and any surviving debris falling into a remote area of the Pacific Ocean. It will be a bittersweet moment, the end of an era, but also a testament to what the station accomplished. The legacy of the International Space Station extends beyond its scientific discoveries and technological achievements. It proved that international cooperation in space is not only possible, but practical. It provided a continuous human presence in space for more than 2 decades. It inspired millions of people around the world and trained a generation of astronauts and engineers who will lead future exploration efforts. The station also changed how we think about living in space. The early space stations were cramped and utilitarian, places where cosmonauts and astronauts endured difficult conditions for the sake of science and national prestige. The International Space Station, while still challenging, has become something closer to a home. Crew members celebrate holidays, watch movies, and video chat with their families. They have learned not just to survive in space, but to live there. This evolution in thinking is essential for the future of human spaceflight. If we are to become a truly spacefaring species, we must learn to make space not just a destination, but a place where people can thrive. The International Space Station has been a crucial step on that journey. Chapter 11: The New Space Age, Commercial Revolution. For decades, space was the domain of governments. Only nations had the resources to build rockets and spacecraft, to train astronauts, and to operate the complex infrastructure needed for space missions. Private companies played supporting roles, building hardware under government contracts, but the initiative and direction came from NASA, Roscosmos, and other space agencies. That began to change in the early 2000s. A new generation of entrepreneurs, many of them enriched by the technology boom, looked at space and saw opportunity. They believed that the high cost of space access was not inevitable, but rather the result of government bureaucracy and lack of competition. They set out to prove that private companies could do it better, faster, and cheaper. The most significant of these entrepreneurs was Elon Musk. After making his fortune with PayPal, Musk became obsessed with the idea of making humanity a multiplanetary species. He believed that the key to this goal was dramatically reducing the cost of space transportation, and he founded SpaceX in 2002 to pursue that vision. SpaceX's early years were marked by struggle. The company's first rocket, the Falcon 1, failed on its first 3 launch attempts. Each failure brought SpaceX closer to bankruptcy. Musk later revealed that the company had enough money for one more attempt. If the 4th launch failed, SpaceX would be finished. On September 28, 2008, Falcon 1 reached orbit on its 4th attempt. It was the first privately developed liquid-fueled rocket to achieve this milestone. SpaceX had survived, and the commercial space revolution had truly begun. The company moved quickly to develop larger rockets. The Falcon 9, first launched in 2010, could carry much heavier payloads and was designed from the start with reusability in mind. SpaceX believed that reusing rockets, rather than discarding them after each flight, was the key to dramatically reducing launch costs. The pursuit of reusability led to some of the most spectacular footage in spaceflight history. SpaceX began attempting to land Falcon 9 first stages on drone ships in the ocean and on landing pads at Cape Canaveral. Early attempts ended in explosions, but the company learned from each failure. In December 2015, SpaceX successfully landed a Falcon 9 first stage for the first time. The rocket descended on a column of flame, deployed its landing legs, and touched down gently on the landing pad. It was a sight that would have seemed like science fiction just a few years earlier. Since then, SpaceX has landed and reflown Falcon 9 boosters hundreds of times. Some boosters have flown more than 20 missions, a dramatic demonstration that rockets can indeed be reused. The company has reduced launch costs significantly, though the exact figures are proprietary. SpaceX has also transformed the market for launching satellites. Its competitive pricing has forced other launch providers to reduce their prices or exit the market. The company now launches more rockets than any other provider in the world, including government agencies. The Falcon Heavy, first launched in 2018, is currently the most powerful operational rocket in the world. It consists of 3 Falcon 9 first stages strapped together, providing enough thrust to send heavy payloads to distant destinations. The first Falcon Heavy test flight captured the world's imagination by launching Musk's personal Tesla Roadster into an orbit that takes it past Mars. SpaceX's most ambitious project is Starship, a fully reusable spacecraft designed to carry large numbers of people and cargo to the Moon, Mars and beyond. Starship is being developed at a rapid pace in South Texas, with frequent test flights pushing the boundaries of what the vehicle can do. The spacecraft consists of 2 stages, both designed to be reusable. The Super Heavy booster, powered by 33 Raptor engines, provides the thrust needed to reach orbit. The Starship upper stage can carry up to 100 people or 100 tons of cargo. When fully operational, Starship is intended to make space travel as routine as air travel is today. Development of Starship has involved numerous test flights, some of which have ended in spectacular explosions. SpaceX embraces this approach, preferring to learn from real-world testing rather than extensive computer simulations. Each test, whether successful or not, provides data that informs the next iteration of the design. SpaceX has also developed the Dragon spacecraft, which carries cargo and crew to the International Space Station. Dragon was the first privately developed spacecraft to deliver cargo to the station, beginning in 2012. The crewed version, Crew Dragon, began carrying astronauts in 2020, ending American dependence on Russian Soyuz spacecraft for access to the station. The success of SpaceX has inspired other companies to enter the space industry. Blue Origin, founded by Amazon's Jeff Bezos, is developing its own family of rockets. The company's New Shepard vehicle has carried tourists on brief suborbital flights, while the larger New Glenn is designed for orbital missions. Blue Origin's approach differs from SpaceX in important ways. Where SpaceX moves fast and accepts failures as learning opportunities, Blue Origin emphasizes careful, methodical development. The company's motto, Gradatim Ferociter, or step by step ferociously, reflects this philosophy. Blue Origin is also developing a lunar lander called Blue Moon, which has been selected by NASA to carry astronauts to the moon's surface as part of the Artemis program. The company sees the moon as a stepping stone to a future where millions of people live and work in space. Virgin Galactic, founded by Richard Branson, has focused on space tourism. The company's Spaceship Two vehicle is carried to high altitude by a specially designed aircraft, then released to rocket to the edge of space. Passengers experience a few minutes of weightlessness and see the curvature of the Earth before gliding back to a runway landing. Virgin Galactic began commercial operations in 2023, offering flights to paying customers for hundreds of thousands of dollars per seat. While the flights are suborbital and brief, they represent the beginning of a space tourism industry that many believe will eventually become much larger and more accessible. Rocket Lab, founded in New Zealand, has carved out a niche launching small satellites. The company's Electron rocket is designed for payloads of a few £100, serving the growing market for small satellites used for Earth observation, communications, and scientific research. Rocket Lab has also begun developing a larger rocket and is working on spacecraft for missions beyond Earth orbit. The commercial space revolution extends beyond launch vehicles. Companies are developing space stations, lunar landers, satellite constellations, and other systems that were once the exclusive domain of governments. Axiom Space is building modules that will initially attach to the International Space Station and eventually form an independent commercial station. The company has already flown private astronaut missions to the station and plans to have its own station operational before the International Space Station is retired. Vast and other companies are also developing commercial space stations, creating what may become a competitive market for orbital facilities. These stations could serve as research laboratories, manufacturing facilities, and destinations for space tourists. Perhaps the most visible commercial space project is Starlink, SpaceX's satellite internet constellation. The company has launched thousands of satellites into low Earth orbit, creating a network that provides internet service to remote areas around the world. Starlink has been particularly valuable in areas affected by natural disasters or conflict, where traditional communications infrastructure has been destroyed. The constellation has also raised concerns about its impact on astronomy and the space environment. The bright satellites can interfere with ground-based observations, and the sheer number of objects in orbit increases the risk of collisions that could generate debris. SpaceX has worked to address these concerns, adding visors to reduce satellite brightness and developing plans for deorbiting satellites at the end of their operational lives. Other companies are developing their own satellite constellations for communications, Earth observation, and other applications. The number of active satellites in orbit has increased dramatically in recent years, and this trend is expected to continue. The commercial space revolution has changed the economics and culture of spaceflight. Launch costs have decreased significantly, making space accessible to more organizations and enabling new applications. The pace of innovation has accelerated as companies compete for customers and investors. The workforce has expanded as new companies hire engineers, technicians, and other professionals. This transformation has not been without challenges. Some companies have failed, unable to develop viable products or find sustainable business models. The rapid increase in space activity has raised concerns about sustainability, including the growing problem of space debris. Regulatory frameworks developed for an era of government-dominated spaceflight are struggling to keep pace with commercial innovation. Despite these challenges, the commercial space revolution shows no signs of slowing. Investment in space companies continues to grow, new applications are being developed, and the barriers to entry are falling. The dream of routine, affordable space access, once dismissed as fantasy, is becoming reality. The implications of this transformation extend far beyond the space industry. Satellite technology is enabling new approaches to agriculture, disaster response, environmental monitoring, and many other fields. The possibility of space-based manufacturing, taking advantage of microgravity and vacuum, could create entirely new industries. And the long-term vision of expanding human presence beyond Earth, of becoming a truly spacefaring species, is more credible than ever before. Chapter 12. The Future, Moon, Mars and Beyond. As we look toward the future of space exploration, we see a landscape of extraordinary possibility. The coming decades promise to bring achievements that will rival and perhaps surpass the great accomplishments of the past. Humans will return to the Moon, set foot on Mars, and take the first steps toward becoming a species that lives among the stars. The Artemis program represents America's commitment to returning humans to the lunar surface. Named for the twin sister of Apollo in Greek mythology, Artemis aims to land the first woman and first person of colour on the Moon, while establishing a sustainable presence that will serve as a stepping stone to Mars and beyond. The program builds on decades of technological development and lessons learned from previous missions. The Space Launch System, the most powerful rocket NASA has ever built, will carry the Orion spacecraft and its crew toward the Moon. Commercial landers, developed by SpaceX and Blue Origin, will carry astronauts from lunar orbit to the surface. Artemis 1, an uncrewed test flight, successfully orbited the Moon in 2022, demonstrating that the Space Launch System and Orion spacecraft were ready for human missions. Artemis 2, planned for the near future, will carry astronauts around the Moon. The first humans to travel beyond low Earth orbit since the Apollo program ended more than 50 years ago. Artemis 3 will attempt the first crewed lunar landing since Apollo 17 in 1972. Astronauts will land near the Moon's south pole, a region that has never been explored by humans. This area is of particular interest because permanently shadowed craters there contain water ice, a resource that could be crucial for sustained lunar operations. Water on the Moon could be split into hydrogen and oxygen, providing both breathable air and rocket propellant. This could make the Moon a refueling station for missions to Mars and beyond, dramatically reducing the cost and complexity of deep space exploration. The Gateway, a small space station in lunar orbit, will serve as a staging point for surface missions and a platform for scientific research. Unlike the International Space Station, which orbits Earth every 90 minutes, the Gateway will follow a highly elliptical orbit that brings it close to the Moon and then swings it far out into space. This orbit requires minimal fuel to maintain and provides access to different regions of the lunar surface. International partners are contributing to the Artemis program, continuing the tradition of cooperation established by the International Space Station. The European Space Agency is providing service modules for the Orion spacecraft. Japan and Canada are contributing components for the Gateway. Other nations have signed the Artemis Accords, a set of principles for peaceful and sustainable lunar exploration. The goal of Artemis is not just to visit the moon, but to stay. NASA envisions a sustained presence on the lunar surface, with astronauts living and working there for extended periods. This will require developing new technologies for life support, power generation, and resource utilization. It will also require understanding how the human body responds to the lunar environment, with its partial gravity, extreme temperatures, and radiation exposure. The moon will serve as a proving ground for the technologies and techniques needed for Mars. Living on the lunar surface, just a few days from Earth, will teach us lessons that will be essential when we venture to a world where help is months away. Mars has been the ultimate destination for human space exploration since the earliest days of the space age. The red planet has captured human imagination for centuries, and the dream of walking on its surface has motivated generations of scientists and engineers. The challenges of sending humans to Mars are immense. The journey takes 6 to 9 months each way, depending on the alignment of the planets. Astronauts will be exposed to cosmic radiation and the physiological effects of weightlessness for far longer than any previous mission. They will land on a world with a thin atmosphere, extreme cold, and no readily accessible water or oxygen. Once on Mars, astronauts will be largely on their own. Communication delays of up to 20 minutes each way make real-time guidance from Earth impossible. Any emergency will have to be handled with the resources and expertise available on site. The psychological challenges of isolation and confinement, far from home with no possibility of quick return, will be unprecedented. Despite these challenges, serious planning for human Mars missions is underway. NASA's Moon to Mars program envisions using the experience gained from Artemis to prepare for the journey to the red planet. SpaceX has made Mars colonization the central goal of its Starship program, with Elon Musk expressing ambitions to establish a self-sustaining city on Mars within the coming decades. The first human Mars missions will likely be exploration-focused, with small crews spending limited time on the surface before returning to Earth. Later missions could establish permanent bases, with crews rotating in and out on regular schedules. Eventually, if the most optimistic visions are realized, Mars could become a second home for humanity, with a self-sustaining population capable of surviving even if contact with Earth were lost. The scientific potential of human Mars exploration is enormous. Robotic missions have revealed tantalizing hints that Mars may once have harbored life, or might even harbor it still in subsurface environments. Human explorers, with their ability to make real-time decisions and adapt to unexpected discoveries, could search for signs of life far more effectively than any robot. Finding life on Mars, even microbial life, would be one of the most profound discoveries in human history. It would tell us that life is not unique to Earth, that the universe may be teeming with living things. It would transform our understanding of our place in the cosmos. Beyond Mars, the outer solar system beckons with destinations that may be even more promising for the search for life. Europa, the ice-covered moon of Jupiter, almost certainly has a liquid water ocean beneath its frozen surface. That ocean, warmed by tidal heating from Jupiter's gravity, could potentially harbour life. NASA is developing the Europa Clipper mission, which will make dozens of close flybys of the moon, studying its ice shell and searching for signs of the ocean below. Future missions might land on Europa's surface, melt through the ice, and explore the ocean directly. Such a mission is technically challenging, but not impossible with current or near-term technology. Enceladus, a small moon of Saturn, is another promising target. The Cassini spacecraft discovered geysers of water vapor erupting from the moon's south pole, shooting material from a subsurface ocean into space. Future missions could fly through these plumes, sampling the ocean water without having to land. Titan, Saturn's largest moon, is perhaps the most Earth-like world in the solar system, despite being utterly alien. It has a thick atmosphere, weather systems, and lakes and seas of liquid hydrocarbons. The Dragonfly mission, currently in development, will send a flying drone to explore Titan's surface, hopping from location to location to study this strange and fascinating world. The search for life is also extending beyond our solar system. Thousands of exoplanets have been discovered orbiting other stars, and some of these worlds are roughly Earth-sized and orbit in the habitable zones of their stars, where liquid water could exist on the surface. The James Webb Space Telescope, launched in December 2021, is revolutionizing our understanding of exoplanets. Its powerful instruments can analyze the atmospheres of distant worlds, searching for gases that might indicate the presence of life. While the telescope cannot directly image Earth-like planets around Sun-like stars, it is laying the groundwork for future observatories that will have that capability. Future space telescopes, currently in the planning stages, could directly image Earth-like exoplanets and search their atmospheres for biosignatures, chemical signs of life. Finding such signatures would not prove that life exists on those worlds, but it would provide compelling evidence that we are not alone in the universe. The ultimate dream of space exploration is interstellar travel, journeying to other star systems. With current technology, such journeys would take tens of thousands of years, far too long for crewed missions. But concepts are being studied that could dramatically reduce travel times. Breakthrough. Starshot is a project to develop tiny spacecraft that could be accelerated to a significant fraction of the speed of light using powerful lasers. These spacecraft, weighing just a few grams, could reach the nearest star system, Alpha Centauri, in about 20 years. They would carry cameras and instruments to study any planets they encounter, sending data back to Earth. More speculative concepts, such as fusion-powered spacecraft or even more exotic propulsion systems, could potentially enable crewed interstellar missions within human lifetimes. These technologies are far beyond our current capabilities, but they are not prohibited by the laws of physics. If humanity survives and continues to advance, interstellar travel may eventually become possible. The future of space exploration will be shaped not just by technology, but by choices we make as a society. How much are we willing to invest in exploring the cosmos? How do we balance robotic and human exploration? How do we ensure that the benefits of space are shared broadly and that space activities are conducted sustainably? These questions have no easy answers, but they are questions worth asking. Space exploration is not just about satisfying curiosity or achieving national prestige. It is about expanding the boundaries of human experience, about learning our place in the universe, and about ensuring the long-term survival of our species. The Earth is our cradle, but we cannot remain in the cradle forever. The cosmos calls to us, as it has called to every generation of humans who looked up at the night sky and wondered what lay beyond. We are the generation that can begin to answer that call, that can take the first steps toward a future among the stars. As we come to the end of our journey through the history of space exploration, let us take a moment to reflect on how far we have come. From the first wondering glances at the night sky to the footprints on the moon, from the earliest rockets to the spacecraft now exploring the outer reaches of our solar system, humanity has achieved things that our ancestors could scarcely have imagined. We have sent our machines to every planet in our solar system and beyond. We have walked on another world and lived in space for decades. We have discovered thousands of planets orbiting other stars and begun to search for signs of life beyond Earth. We have transformed our understanding of the universe and our place within it. And yet in many ways, we are just beginning. The solar system awaits exploration, with countless worlds and moons that have never been visited. The search for life beyond Earth is entering a new and exciting phase. The dream of becoming a multi-planetary species, once the province of science fiction, is becoming a realistic goal. The story of space exploration is ultimately a story about what it means to be human. It is about our curiosity, our courage, our creativity, and our determination to push beyond the boundaries of the known. It is about our ability to work together, across nations and generations, toward goals that transcend our individual lives. As you drift off to sleep tonight, perhaps you will dream of the cosmos. Perhaps you will imagine yourself floating in the silence of space, looking down at the blue marble of Earth, or out at the infinite darkness studded with stars. Perhaps you will dream of walking on Mars or sailing through the clouds of Titan, or journeying to worlds we have not yet discovered. These dreams are not idle fantasies. They are the seeds of future achievements. Every great accomplishment in space exploration began as a dream in someone's mind. The rockets that carried astronauts to the moon were first imagined by dreamers like Tsiolkovsky and Goddard. The rovers exploring Mars today were once sketches in an engineer's notebook. Your dreams matter. The next generation of space explorers is out there right now, perhaps listening to these words, perhaps imagining their own journeys among the stars. The future of space exploration will be shaped by their dreams and by the choices we all make about what kind of future we want to create. So dream boldly. Dream of the moon and Mars, of Europa and Titan, of worlds orbiting distant stars. Dream of a future where humanity has spread beyond its home planet, where our descendants look back at us as the generation that took the first steps toward the cosmos. The universe is vast beyond comprehension, filled with wonders we have only begun to discover. And we are part of it, children of the stars exploring our cosmic neighbourhood. What a privilege it is to be alive at this moment in history, when so much has been achieved and so much more lies ahead. Thank you for joining me on this journey through the history of space exploration. I hope it has brought you wonder and peace, curiosity and calm. As you drift off to sleep, know that somewhere out there, spacecraft are still exploring, still discovering, still pushing the boundaries of the known. The story of space exploration is not finished. It continues with every new mission, every new discovery, every new dream. And in some small way, it continues with you, with your curiosity and your wonder, with your dreams of what lies beyond. Sleep well, dear traveller. The cosmos will be there when you wake, waiting to be explored. And if you enjoyed this journey through the history of space exploration, please consider subscribing to the channel and leaving a like. Your support helps us create more content like this, more journeys through the wonders of the universe. Thank you for being part of this community of dreamers and explorers.